Hi everyone, welcome to the last video of our Gauss's law unit. We have analyzed how Gauss's law can be used to determine the electric field due to spherical charge distributions and planar charge distributions, as well as cylindrical charge distributions. Here we're going to bring together some of those results to revisit our understanding of how conductors must behave when they're in electrostatic equilibrium. That means that the charges are not in the process of moving around. So the electric field of a conductor in electrostatic equilibrium must be due to the charges on the surface. Otherwise, charges would move due to a net electric field, and the result of this would be that eventually they would move into configurations where they wouldn't be moving anymore, but that would mean that there wouldn't be any electric fields inside of the conductors. So the electric field must also be perpendicular to the surface of our conductor. If this was not true, there would be parallel components of the electric fields, and these parallel components would cause the charges to move around until they have configured themselves into an arrangement where there are no more parallel components of the electric field causing charges to move around. And usually this happens very quickly, I might mention. Now, one can also use Gauss's law to show, using a small Gaussian pillbox with parts above and below a conducting surface, that in the area close to the surface of a conductor, the electric field is about equal to the surface charge density over epsilon naught, where that surface charge density is the local surface charge density in that area of the surface, as long as you are real close to the surface of your conductor. Now you might wonder, wait a second, I thought we just did this earlier in a previous video and found that it was e over 2 epsilon naught. Well, here's the thing. That was in a situation where you had a sheet of charge, where the electric field was going away from the sheet in both directions. But in the case of a conductor, the electric field isn't going into the conductor, remember. It's only going out of the conductor. So as a result, basically the electric field lines that would have been inside of the conductor, now they're directed outside of the conductor. So you're greater by a factor of 2. So here's kind of a depiction of such a situation. And remember that inside of your conducting medium, the electric field is always 0. And then the electric field at the surface is going to be perpendicular to the surface, where the charge has all congregated at the surface. Now, what that means for the charge distribution near these corners is actually something that we're going to examine in more detail in the next unit when we talk about the electric potential. And one of the big features of conducting surfaces is that they are equipotential surfaces. The electric potential is the same everywhere along the surface. So a result is actually going to turn out to be that charge is going to congregate near these corners. But that's something that we're going to examine in more detail in the next unit. What about conductors with holes? These types of problems often show up on the AP exam, both in the free response part and on the multiple choice part. So the question is, what is the electric field everywhere in a situation like this? So to figure out how to answer this, it depends on whether or not someone has actually physically placed extra charge inside of these cavities. So in general, you start with a condition where the fact that the conducting medium itself must have no electric field inside of that conductor. So since there's no net charge inside of the conductor unless somebody is actually holding it there, a hole inside of a conductor must have no net charge and thus no electric field inside of it, unless somebody is literally placing extra charge there and holding it there. So unless that's the case, the cavity will contain no electric field. Now, what about the situation where somebody has placed extra charge there and is holding that extra charge there? So if it's placed inside of a hole in your conductor, the opposite charge will flow toward the surface of that hole so that the electric field remains 0 inside of the conducting medium. In other words, the electric field in the metal itself inside the surface of the conductor is still going to be 0. So that's one of the big results, because remember, we know the electric field must be zero inside of a conductor, otherwise it's going to end up forcing charge to move around until it becomes zero. In other words, it wouldn't be an electrostatic equilibrium. So as a result, since that opposite charge must come from somewhere, it must have come from the surface of the conductor. So in a situation where there's no net charge, then there's nothing special going on at this inner surface, and the electric field there is going to be zero. But if you try to put charges inside of this, then some of the opposite charge will end up flowing from the surface to help to cancel that out, to keep the electric field inside the conducting medium as zero. Now, here's a situation where you place a conducting shell in between a couple of parallel plates that have a large electric field. Well, what ends up happening is, because this is a conductor, the charges are free to roam around, the charges are going to rearrange themselves such that they end up kind of canceling this in effect inside. So for example, the positive charge plate is on the left. Well, the negative charges are going to be attracted to that positively charged plate, leaving behind positively charged areas which are preferentially attracted to the negative plate. The result of that ends up being a counter-electric field from left to right inside of the conducting shell, canceling the electric field that goes from right to left that's due to the parallel plate capacitor. The result is that the electric field inside of this is zero, as long as nobody is holding any net charge inside of that. So effectively, you get a shield, and we have a name for that we have discussed already in this course. That is the Faraday cage. That's why you're safe inside of an automobile if it's getting struck by lightning, as long as the car itself is made of metal. Now, what if you have a charge hanging around, or you pin a charge there? Well, as we mentioned, that let's say you have a positive charge here, that positive charge is going to attract negative charges, which are going to flow there because it's a conductor. They can, but where do they come from? That's going to leave behind a net positive charge at the surface. So if this was originally an uncharged conductor, at least at the surface, and you put only this positive point charge, little q, inside of here, that's going to attract negative charges, which must come from somewhere. They've got to come from the surface, leaving behind net positive charges at the surface, which are going to add up to a total charge of positive little q at the surface. So that's kind of cool. So that's something to keep in mind, not only in cases where you have a neutral conductor, but also cases where you have a conductor that actually already has charge at the surface. And it's these types of situations that sometimes show up on the AP exam. So let's say you have a spherical conductor that is neutral, but you have a cavity in which suddenly appears 2 microcoulombs of charge. Well, that means that a charge of negative 2 microcoulombs is going to leave the surface of that sphere, such that if you make any sort of Gaussian surface around that cavity, it's going to contain, you know that the electric field in your conducting medium is zero, because the electric field in any conducting medium is always zero. So imagine a Gaussian surface around. In fact, we could even imagine that this little pink ring here is a Gaussian surface. The Gaussian surface around this must have an electric field of zero, which means an electric flux of zero. Well, the only way it can have an electric flux of zero is if the total charge contained inside of this imaginary Gaussian surface is zero. That's Gauss's law. So that tells you exactly how much negative charge ends up coming here from the surface. It's exactly the same amount to balance the positive charge. So again, the logic with this is you use the fact that the electric field in a conducting medium is zero. You place your Gaussian surface in that conducting medium. You know that since the electric field is zero, the electric flux through your Gaussian surface must be zero. Since the electric flux is zero, that means it contains no net charge. So whatever charge you pin inside of the cavity must be canceled by opposite charge that accumulates at the inner surface of the conductor, and basically the surface of the cavity. Okay, so the result here is that if you pin 2 microcoulombs of charge inside of your cavity in a neutral conductor, that attracts negative 2 microcoulombs of charge from the outside surface of the sphere, and that ends up going to the surface of the cavity, leaving a charge of plus 2 microcoulombs on the surface of the sphere. Because the surface had been 0, negative 2 microcoulombs has left. A negative leaving means that a positive remains. 0 minus negative 2 leaves you with positive 2 on the surface. In other words, whatever the shape of your cavity inside of a conductor, whatever charge you put there is simply going to be charge that effectively appears on the conducting surface. And this happens, it spreads itself out uniformly, hiding any knowledge of the cavity's shape. That's kind of cool. Now, what if you have a conductor that has plus 160 nanocoulombs of charge, and it has a cavity created inside of it in which suddenly appears negative 20 nanocoulombs of charge? Somebody just somehow magically brings negative 20 nanocoulombs of charge into that cavity. Well, that means that 20 plus 20 nanocoulombs of charge is going to rush toward the surface of that cavity, and that 20 nanocoulombs of charge has got to come from somewhere. The only place it can come from is the surface of the conductor. So 20 nanocoulombs of charge has left the surface. The surface used to have 160 nanocoulombs. If 20 nanocoulombs leaves, then that leaves the surface with 140 nanocoulombs. And again, notice that what's left at the surface is equal to the total charge of this object. In other words, it reflects the fact that the surface used to have 160, but there's negative 20 inside of the cavity. Well, that's a total of 140 nanocoulombs, but that's simply what is left on the surface. So again, the charge on the surface hides any knowledge of what's going on inside of the conductor. So, a summary for dealing with conductors in electrostatic equilibrium is that the electric field must be 0 at all points within the conducting medium, within the volume of the conductor itself. Second, any excess charge must reside entirely on the exterior surface of the conductor. Third, the external electric field at the surface is perpendicular to the surface and actually has a magnitude of eta over epsilon naught, where eta is the local surface charge density at that point. And fourth, the electric field is 0 inside of any hole within a conductor unless there is charge brought into that hole. So that actually brings us to the end not only of our discussion of conductors in electrostatic equilibrium in this general overall discussion, but it brings us to the end of this overall discussion of Gauss's law. So that's the end of our little mini unit on Gauss's law. Thank you all for watching. If you have any comments or questions, post them in the comments on YouTube. And I hope to see you all back when we begin the next unit on the electric potential. Thank you for watching.